Hi, welcome to our assignment 5 presentation. This is the final assignment. It's on the graph data structure. What we created here is a social media graph. So individuals would be the nodes, and the connections or friendships between those people would be represented by the edges. We have iGraph, which is our interface. Add edge, remove edge, get number of nodes, get number of edges, and get neighbors, which gets your immediate neighbors, which would be someone who you know directly and are friends with, connected to in a social media sense. So not a friend of a friend, but your direct friend. Now we have created three representations for this graph: an adjacency list, which is the same as in assignment 1, an adjacency matrix. This one is something new that we created, and we also have our edge list representation. So if we go to our assignment, our PDF report, we can see a simple representation of this. This graph is bidirectional. R1 is an undirected graph because if A is friends with B, B is also friends with A, direction is not required. Our graph is also unweighted because, well, a friendship is a friendship. We gave a default value of 1 for all of these weights, which, that creates an unweighted graph, and we just don't need that for our social networking graph. Our implementation has the capability of adding weight as a parameter, but we currently don't make use of it. And that would be in social media graph, where we have the graph edge weight. Now we go to our next section. Forget if I mentioned it, but we have the Java doc and the UML diagrams. They're ready. The UML diagrams might actually be good to look at here for once. It's a comprehensive overview of everything. We have the iGraph data structure, which helps create our 3 different implementations. Of course, the edge list implementation requires an edge, and it all uses the social media graph. What's going on here now in these different representations is very clear here. So with the matrix, we have all the nodes here. A is connected to A is connected to B, and A is connected to C via these edges. C is not connected to anything. I love the adjacency list representation because it's quite clear. It just has all the nodes, and if a node has a connection, it is represented on the right hand side, and the node in question is on the left hand side. Now the edge list representation is a representation of the edges, so not the nodes, but simply the edges. So since our task here is to find the shortest distance between 2 given nodes, we would expect that the adjacency matrix and the adjacency list representation are faster than the edge list. Now, what is a bit more interesting is which is faster, the adjacency list or the adjacency matrix, and it really depends on the context. So if we go here, the adjacency matrix in blue and the adjacency list in red, we see that it's pretty close, but the adjacency matrix tends to be a bit faster. Now this is the case where we keep the number of edge constant, but we manipulate the number of nodes or users in the network. So what I'm saying here is that each new person that joins our social media has 100 friends, 100 connections. So if more people join the network and they all have 100 friends each, which of these would be faster? We're using Dijkstra's algorithm to calculate the shortest distance between 2 people. And the point of this is, you could use this for multiple instances. You could use it for recommending friends, recommending groups for users to just join, and seeing how many connections someone is away from someone else, which is something you see on LinkedIn a lot, whether they're your second connection or your third. a friend of a friend or a friend of a friend of a friend, etc., etc. The reason this always works and it always returns a root, and it's not the case that we don't have a root. We use something simple called 6 degrees of separation. So basically the probability that no root is found is virtually zero, because there'll always be a friend of a friend or a friend of a friend of a friend who knows the person who you're trying to reach, which would be the destination node. Now, yeah, as I was saying, as we see here, the adjacency matrix is faster until we reach a certain threshold. So what happens in this representation is that as the number of edges increases, the adjacency matrix becomes a more optimal solution, and the adjacency list falls down in efficiency. And this is because the adjacency list has to keep track of all these edges connected, and it's just more work the more edges you have. Whereas the adjacency matrix, it's constant lookup time to find anything. And the way it's set up is, well, you're going to add zeros or ones. So yeah, it won't affect the size of this, but the size of this will increase if you have more edges. The size of the adjacency list will increase. So that's for the edges. And for the users, as the number of users increases, the adjacency matrix becomes a less efficient solution. Given the very important constant that the number of edges or the number of connections that each user has remains constant. So here we left it at 100. So each new user that joins will always have 100 connections. If we have more users, what happens? The adjacency list becomes more ideal. And this is quite clear from here that, if we had more users here, the efficiency of the matrix goes down exponentially, not exponentially, but quadratically at a rate of n squared, the number of nodes squared, because if we had 10 users, it would be 10 squared, which would not be really too great. But if we had 10 users for the adjacency list and the number of connections remains constant, well, it wouldn't be too bad. For every new user I add, I just need a new line here. But for every new user I add here, for every new user on the x-axis, you also need its corresponding y, and yeah, it becomes a squared factor larger. So it kind of adds up why this is happening, and this is a good rule of thumb. So what we're always trying to balance here is the number of nodes squared and the number of edges, because the number of nodes squared represents the adjacency matrix, and the number of edges would affect the adjacency list. So if we go back to our solution, we will find that, let's say we make the number of friends 1. We won't actually find the destination node because not enough people are around. So in this case, we have 300 friends and 1,000 users. And this is the amount of time it takes. So yeah, basically the edge list isn't very good because we're trying to find nodes, so it will always be quite slow. In this case, the matrix took a bit longer than the adjacency list. And let's say I wanted to make the matrix faster, probably lower the number of nodes. And we should find, it's very random, but because of the generating factor, but we should find that the matrix starts performing better One thing to note here is that I had to append extra RAM in my run configurations so I don't run out of memory while doing these calculations. Now this one is running rather long, so I will stop it. Well, I mean, this makes sense because you can't really have 300 friends if you have 100 users. Well, I guess not enough users to make it very viable. So this would be basically the perfect number for the matrix. So I did a bit of a cheat here because yeah, if you think about it, if you all have 300 friends, basically all of these will just be ones, so the matrix is being used very efficiently and the adjacency list is being used very inefficiently, but it demonstrates the point that we're trying to get across here of when the matrix is better and when the list is better. We also have some tests here, comprehensive tests to make sure that all of our graphs work properly, and also to make sure that our shortest path runs properly, that it finds a path when it's supposed to, and if no path is found, it returns the correct -1. So yeah, no, that should be basically everything. And we'll just take a final overview of these. Make sure I got everything. Yeah, no, that's it. So yeah, thanks.